Greetings. We spoke yesterday, well last time anyway, about combining functions using addition, subtraction, multiplication, and division. This time we're going to talk about function composition, which is the rest of this section. So first we're going to talk about what composition actually is. We're going to do an example numerically. We're going to build a table to explain what composition actually is underneath. Then we're going to learn how to combine two functions to create a composite function. Then determine the domain for our composite function. There's a couple steps to that. And also I'm going to show you an example where I decompose a function, because that's something you'll be required to do. As far as what function composition actually is, up until now we've combined two functions as sort of equals. We'd add one to the other, or we'd divide them, things like that. In function composition, you're actually you're doing one function before you do another function. So there's a priority or an order to it. We denote function composition using one of two notations. This is one of them. This we read as f of g of x. In this case, you're going to evaluate g. You're going to take the answer and stick it into f. Now this is the same as writing f with a little circle, g, f of g of x. Means the same thing. I like this one better because it gives you a picture of the fact that you're sticking g of x into f. It means the same thing though. So in this case we're doing f of g of x. So to get a picture for what that actually means, I'm going to make a table. I'm going to pick some x values. I'm going to put them into g and get an answer. I'm going to take the answer for g and stick it into f. And so that will be my third column. So if I start with 0, when I stick 0 into g, I get 0 minus 4, which is negative 4. I stick negative 4 into f, I square it, I make 16 plus 1 is 17. Similarly, if I stick in 2, 2 minus 4 is negative 2. When I stick that into f, I'm going to get 4 plus 1, which is 5. If I stick in 4 into g, I'll get 0. 0 squared is 0, so then when I add 1, I get 1. And I could keep going. I'll stick in 5 as well. That gives me 1 from g. I take 1 and stick it in here, and I get 2. So that's really what function composition looks like. You're sticking your x into the inside function, and then you take the answer to that and put it into the other function. This is a, like I said, numerical explanation. We can actually shortcut this process. Rather than having two different functions we have to use, what we want to do is make a new function that does the job of f of g of x without taking so many steps. And the way we do that is we actually take the equation for f of x, x squared plus 1, and we're going to replace the x with g of x. And what that means is you go through, and any place where there's an x in the equation, you're going to put g of x in there. So if I do that literally, I'll stick g of x right there. So this x became g of x. I'm squaring it because I was squaring the x. If you want to write that out so the function becomes usable, you replace this g of x with its definition x minus 4. And to do a real job, we should then simplify this. So I'm going to expand this square. If I FOIL, I'll get x squared minus 4x plus 16, and then of course the plus 1 from the end. So x squared minus 8x plus 17. Now this function is the same thing as this column. It'll go straight from these numbers to these numbers. So if I stick in 0, you'll see 0 minus 0 plus 17 goes right to 17. If I stick in 2, I get 4 minus 16 plus 17, which is 5. If I stick in 4, I get 16 minus 32 plus 17, which is 33 minus 32, which is 1, and so on. So this is one function that does the composition job. So that's finding a composite function. These are polynomials, so their domains are all real numbers, which means the domain of the composite function is all real numbers. But sometimes we combine two functions that do not have such easy domains. So if I take f of x to be 3x minus 1 over x, and I take g of x to be 2x plus 4, and I look at their domains, this one is a line, so its domain is all real numbers. But this equation, f, is not allowed, x is not allowed to be 0 for its domain. Oh dear. Domain. X is not allowed to be 0, which means that I have to be careful about what numbers I'm sticking into f. When I'm dealing with f of g of x, however, it's not x that I'm sticking into f. It's the answer to g of x that I'm sticking in. So I no longer can say that x can't be 0. If I stick 0 in here, what I actually stick into f will be 4, not 0. I need to figure out what I stick in here in order to cause a problem. So in this case, because I'm doing composition, instead of x not being 0, it's g of x that can't be 0. Once I establish what it is that g of x can't be, I can produce from g of x an equation, or in this case inequality, that I should be able to solve. 2x cannot be negative 4, which means what x actually can't be is negative 2. And that gives me the domain for the composite function. So I have to make sure it's a number I can stick into g, and I have to make sure that it's a number that after I stick it into g, the answer will fit into f. Let's do one slightly more complicated. So if I propose a new f of x with a square root of x minus 1, and then g of x is equal to x minus 1 squared, then when I make f of g of x, I'm going to take this x minus 1 squared and stick it in here for x. So x minus 1 squared minus 1. Again, tidying this up, the x minus 1 squared is going to be x squared. It'll be minus x when I FOIL, which is minus 2x, plus 1, and then the minus 1 from the end, which are going to cancel, so I'll have the square root of x squared minus 2x. As far as its domain, the domain for a polynomial, like g of x here, is all real numbers, so it's fine. But the domain for f is that the inside of a square root has to be greater than or equal to 0. So the domain here, x has to be greater than or equal to 1. But when I do the composition, it's not x that has to be bigger than or equal to 1. It's g. So g of x has to be greater than or equal to 1 in order to be able to stick it into f. Solve this then. G of x is x minus 1 squared. I'm going to take the square root of both sides, but when I take the square root of a square, it actually makes the absolute value. I think in the past we've done this with equations, and we just said put a plus or minus, which isn't really wrong. Although if you remember when we solved these, with the equations, the plus and the minus, the equation doesn't cause a problem. But when we switch this to plus or minus in an inequality, we actually need to invert the minus 1. So the plus 1 stays as greater than 1. But when we do the minus 1, we have to switch the inequality around. So over here, x is greater than or equal to 2. And over here, x is less than or equal to 0. So here we have x is less than or equal to 0, or x is greater than or equal to 2. Either one of those sections will fit into the domain. If you prefer interval notation, that's negative infinity to 0, and then again from 2 to infinity. The last thing I need to show is decomposing a function. When we have a function, well, I'll use h. If we have a function and we want to decompose it, what that means is we're going to assume that it was originally two functions that got stuck together. You want to look for a function inside and a function outside. In this case, I think the inside function should be x plus 2. So I'm going to call that g of x. And the outside function, f of x, is what we stuck that into, which is the 1 over x squared. And you can see if I stick g into f here, h is what I'll get. And that's called decomposing a function. This should be what you need to get started on your homework. Please feel free to ask if you have any questions.